Now, in the continuation of the properties, we have seen periodicity, linearity, circular symmetry, which was not in Z. So, we have taken the how shifting is possible and how shifting is in circular format. Now, the next is the circular convolution. Convolution is very important property just because we can't multiply directly two sequences in time domain. We know when we have studied the linear convolution, that time when we are dealing with the two sequences, they are moving related together and both are varying. So at that time the multiplication of two sequences is difficult, so we use convolution. And with their length of the sequences, we can have linear convolution. But we are dealing circular convolution with the limit of 0 to n-1 sequences and samples. Then in Fourier transform, the circular convolution is one kind of theorem. And it states that this property states that this is the fourth property of this DFT. This property states that multiplication of two DFTs is equal to the circular convolution in time domain. If we pre-process the xn values, xn is the time domain sequences, and discrete time domain sequences, when they are convolved, that their individual transforms can be multiplied and then reconstruct as finding out the inverse discrete Fourier transform for the product of these two sequences. We can calculate the value of the convolved sequence. I repeat here again. Then if we have two finite length sequences x1n and x2n, or it may be the infinite values, infinite length, then we'll take for DFT for finite sequences. And if we take finite sequences, then in time domain they are convolved circularly, because we have taken the periodic sequence, and periodic sequence are repeating, and if they are repeated, then we can do it circular shift. And if circular shift is there, then we'll have less memory space required, because we use the same length of the x1 and x2n. With the same length, we can have the product of these two sequences, which is not possible with any other multiplication. So, it is necessary that these two sequences in time domain, when it is periodic, finite length and circular, is convolved in circular convolution. So, we get this x1n and x2n. This circle n is called circular convolution. In linear convolution, we used to have star, x1n star x2n. So, this was the convolution we studied in something in all other systems. So, this is not, because we are taking periodic and repeated in circular shift. So, this convolution is possible with circular convolution. So, if we get this circular convolution, the equation is that n is for the samples n 0 to n-1. We are shifting it x1n, and the other one is circularly shifted with m-n. So, it can be, because it is circularly shifted, it can be calculated as a modulo index modulo n, and we know how we solve it, index modulo n. So, this is the circularly shifted and one is the x1n. When we take its circular convolution, then we get this x3n. Okay, and x3n sequence will give us x3k DFT format. So, whatever our requirement, we can have this x3n and x3k. Now, there is one more that this property says that x1n is DFT x1k x2n discrete time sequence with n point DFT x2k with the same length, then circularly convolved sequences x1n and x2n will be equal to the Fourier transform x1k and x2k product, the multiplication of two DFT sequences. It is so simple. So there are two, we can solve this circular convolution to get this value x3 and an x3k as per our requirement. We can have this circular convolution in time domain, and to get this x3n, then transform it DFT with n-point sequence, then we'll get x3k. So to process, we get this x3n. The another method, when we are going through the transformed values, that x1k, take x1k individual x1 sequence, then take x2k individual x2k, then product it. We'll take this x3 is x1k into x2k directly. Then we multiply it. We can multiply it in the frequency domain, of course. That was also in the time domain. Convolution says x1z into x2z directly. So here we also have that x1k transformed values of individual sequence, and then x2k transformed values of the x2k. We can have product of it, that will be x3k. Then we IDFT to x3k, so we get x3n. This x3n and this x3n will be same. This is the circular convolution property. So today we discuss about how to take this circular convolution, because it is very conventional method, and practically when we have in the mobile communication GSM, what are be decoders, and so many cyclic redundancy codes, we used to have that circular convolution there also. So it is very important. So you should know that how we convolve two sequences, finite duration, periodic, and repeated in n samples. So how we convolve it. So let us discuss about the circular convolution. The equation says x1n into 1 should be, when we are convolving, convolution is being done, the one sequence should be shifted. And how it should be shifted? It should be shifted in circular manner. So this equation, we can have one problem. No? With the suitable example, I am giving you this, with suitable problem, I am giving you this concept of circular convolution. See, to perform the circular convolution of given two sequences, x1n is 2, 1, 2, 1 and x2n is 2, 1, 1, 2, 3, 4. So just we are plotting this in a circular form. I am giving you this graphical representation. You can have all the calculation with this equation x1n, x2 modulo index calculation. So index modulo calculation, I have already explained how to calculate this index modulo. What is this? Can be written as x n minus k n. So it can be written as like this. So this can be calculated in this manner. I have already explained this. So this is the calculation of modulo n, and this modulo n calculation is shifting of the sequence here and multiplied with this x1n. Then we can have this problem. So I am graphically representing it. When periodically sequence x1n is this, so I just plot it. We assume that the anti-clockwise plotting is the positive way of plotting the x1 sequence and x2 sequence. So here we take this 4 and n is 4. So we are taking this x0, x1 anti-clockwise. x0, x1, x2 and x3. x0, x1, x2 and x3. So the value of x0 is 2, x1 is 1, then x2 is 2, and x3 is 1. So I've plotted this sequence x1 n anti-clockwise. Okay. Similarly, in this k value x2 n. So this sequence I am plotting x0, x1, x2, x3. 1, 2, 3 and 4. So this is the simple plotted on circular circumference of any axis of n. Okay. Now the next is how I think I just review the process. If you know the step of circular convolution, what was that? We had, like, I just remind you, to get this circular convolution, what we used to do, the steps we used to do: first folding, second shifting, third step multiplying, then fourth step sum of product. To multiply this, to execute this equation, the sequence is first folded. We are actually shifting this value. We are keeping one sequence as it is. So another one is shifting. So here this folding, then shifting by one step by step, then multiplying with this sequence, and then sum of the each sequence, shifted sequence, the product samples, we sum together. That will be the value of 1. So if you remember the convolution, then this is the step. So okay, now we repeat it here. We'll repeat. This is the plot of the sequence. Then folding. So this is folding sequence. Okay. Folding sequence of x2. So x2 of minus n. So I have shifted x1 is this, and I have taken something this, in one page. You can also solve it with me, that this is x1n, and I have taken the axis similar, just shifted sequence. Then x2n I am taking. So all these shifting is with x2. So I am drawing here this all six shifting x2 and x1, and we'll multiply this, then this, then this, and then so on. Okay. So let us shift x2. 1, 2, 3, 4. So I have already plotted x0 anti-clockwise initially. x0, x1, x2, x3. Now for having the folding sequence, we'll plot it anti-clockwise. To get the x of minus n, what we are plotting this x2, x0, x1, x2 and x3 anti-clockwise. This is folder sequence. So for our first step was folding. So we have folded this sequence. So this is for value x equal to 0. So we are calculating actually x3 by multiplying it. So this is x3n for x3 0 value. Now our target is to get the product sequence x3n for xn equal to 0. So this is x3 0. This is x3 0. Just product 0 with 0, this value with this one, then this value with this one, and this value with this one. So I write here the value 1 into 2. This is 2. Then 4 into 1. This is 4. Then 3 into 2. 6. And 2 into 1. 2. And then we'll take, what is our fourth step? Then sum of all the product samples. It means 2 plus 4 plus 6 plus 2, that will be equal to 14. So x 0 value. I repeated, we have shifted it for n equal to 0 and making the first folder sequence and then this folder sequence will be shifted with one step again and again. Okay, so initially we have considered the direction of plotting the sequences in anti-clockwise direction. This is the original value of x1n and x2n. Now for folding, we have shifted this value in anti-clockwise. So we have this x0, 1, 2 and 3. So anti-clockwise we have taken this value. Now the next step is multiplying with this x1n. So x2n and multiplying with this x1n. So value of this x0 with this x0, then this value, then this value and then this value. So we'll multiply it with the 4 samples, and we have written here the 1 into 2, 4 into 1, 3 into 2 and the 2 into 1. So I have written these values, and the fourth step is sum of all these 4. So this is 2 plus 4 plus 6 plus 2 will be equal to 2 plus 4 plus 6 plus 2, that is 14. Now I take step shift by 1. We are shifting this folder sequence. So again, as this is our for this one shifting, we are shifting this in the anti-clockwise. So this will be x0, it was there, and we shift it anti-clockwise. We are unit step shifting as we have drawn the sequences here. So this 0 will be shifted to here. So see that this x0 will be shifted to this value. So now this by one step it is x0, then shifting this x0, then this one value is shifted to 1, then this value is shifted to here 2, and so one step shifting to the clockwise. Okay, and I have written the values as it is. 1, 2, 3, 4 we had, so it is shifted. Now multiply it. 2 with this value 2, so we have 4. 1, this value 1, so it is 1. Then 4 with into 2, so it is 8. Then 3 into 1, so it is 3. Now fourth step is sum of all the product samples. So that is 4 plus 1 plus 8 plus 3 will be equal to 16. So this is the answer. Okay. Now again we shift it by 1. So we shift it by 1 unit. So we get here x2 minus n. Actually we are shifting and we are getting this modulo of in this manner. Okay. And this capital N is 4, so it would be 4. So this is the shifting. Okay. This step is x2 2 unit shifted. So earlier we have x0 here, then we have shifted 2 unit, so that x2 is there at x0 anti-clockwise. So we have value I have written here 1, 2, 3 and 4. Now we multiply this 3 by this red sequence. So it is 3 into 2, 6, 2 into 1, 2, 1 into 2, 2 and 4 into 1, again 4. So value for 2 unit shifting, sum of samples, that is 6 plus 2 plus 2 plus 4 will be equal to 14. Okay. This is the way. I think it is in the frame. Now again shifting for 4 steps. 1, 2, 3, 4. So this is for x modulo of n. We are taking this. This is actually shifting. So 3 unit shifting. So 3 unit shifting I have written here again anti-clockwise, and now I multiply this 4 into 2, 8, then 3 into 1, 3, then 2 into 2 is 4, and 1 into this 1 is 1. Then again fourth step is sum of all these product sequences. So this will be 8 plus 3 plus 4 plus 1. That will be again 16. So what is circular convolution answer? X3n is 14, 16, 14, 16. This is our answer. I think you understand the concept of plotting the values. I again brief in 2-3 lines that we have sequences xn and x2n. We have a plot here anti-clockwise initially. So it is we are taken the positive direction in anti-clockwise. So this is x0, x1, x2, x3. x0, x1, x2, x3. So these are the two basic equations given. Now we are by the equation we know that to multiply we are shifting one sequence. The step of circular convolution says first find the folder sequence, then shift it by unit 1 step by step, unit 2, then unit 3, and then shifting and multiply with the sequence x1, another sequence, and then sum of the 4 steps, sum of all the products samples for getting the individual value. So when we have folder sequence, it is x0. When we shifted by 1, this is x1. Shifted by 2, it is x2. Shifted by 3, it is x3. So 4 sample and multiplication of 2 sequences with length n, we are having the product of circular convolution, that is x3n 14, 16, 14, 16. Now the step says as we get this x3n, then compute its DFT if we want x4. Otherwise no need to have, because we have to process and we have to deal with the x3n. So circularly convolved, and this is the x3n. If we go for the another method, then individually transforms can be calculated. You know how to calculate the Fourier transform, and then take its product. Then after taking product, the x3k will be that the Fourier transform of the x3 sequence, and then calculate its inverse discrete Fourier transform, and then get x3n. This is the theoretical computation what we have other than this circular convolution procedure. So I just briefly, this is one example of circular convolution. You can have one set of examples, so many values of x1 and x2 in any of the reference books, like in Oppenheim Scheffer and in Procase and in Mitra, and there are so many authors very nicely define the Fourier transform, and we can have different kind of steps. So if we are not going through this circular shifting, then this circular convolution is calculated in the manner that x1n, x2n, suppose this is x3n actually. So its DFT will be x1k product x2k, where x1n has its DFT x1k with the same length, then x2n as DFT endpoint DFT with the same length x2k, and take its product to get this x3k, that will be x1k dot x2k. So after calculating this Fourier transform with the equation n equal to 0 to n minus 1, take x1n and e to the power minus j 2 pi k n by n. So this will be the x1k. Similarly, it will be x2k. We can have and take the product of these sequences. Answer. We'll get the sequences x1k, then x2k, and then take its product. Multiply it. So multiplication of two DFT sequences. Two DFTs. Multiplication. So we'll get this x3k, then solve it for getting xn. So this IDFT equation, I know that x3k we have achieved from here will be calculated 1 by n. Don't forget the sample. Then k equal to 0 to n minus 1 xn. Sorry, I am calculating here xn. x3n small n. IDFT. And that will be your answer, x3n. So this is circular convolution, is very important property, the very significant property of DFT. And earlier, now we have so many modifications in the convolution property, in compression and some coding theory practically. But this is the conventional circular convolution which utilizes the memory space, the bit space. We have the length of the bit will be same, 4 into 4. We have multiplied these two and still we have in the answer the same length. So the circular convolution gives you a significant property of discrete Fourier transform. We'll see the remaining properties in the next session. Take care. Thank you.